Hello. In this video, we're going to review a few aspects of transfer functions, including combining them, stability, and then go through an example of deriving a transfer function from a process model. So just as a quick review, we define a transfer function to be a function in the Laplace domain. So transfer function is written as g in the Laplace domain. This is equal to an output divided by an input. So the transfer function relates how the input affects the output. And again, this is in terms of deviation variable. So these are in deviation variable, which is essentially the variation or the deviation from the steady state value or the initial value. So we can have a transfer function that relates any input to any output. So if we have an input in the Laplace domain and we know the transfer function, we can determine what the output is, and we can represent this. We typically represent this using like a logic flow chart, and we can write it in terms of a generic transfer function. If we wanted to, we can actually write the transfer function in the box. So for example, if it's a first order process, we could write in here kp over tau ps plus 1, and so this would be the transfer function that relates how the input y of s or how the input u of s affects the output. Now if we assume that we have a step change in the input, so a step change for an input would be something like u of s equals a over s. So this comes from just a constant step at time equals 0. So from this, essentially we know that the g of s up here, so g of s equals y of s over u of s, so we can solve for the output in the Laplace domain equals the transfer function times the input, which in this case was kp over tau ps plus 1 times a over s. All right, and then we can use this, or at least from this form of the transfer function, we can assess things like stability, and we can also use this to take the inverse Laplace and determine what y of t. And remember that because this is in terms of deviation variables, when we take the inverse Laplace, we will determine, I'm going to call this y hat of t. And again, we can just use the table to determine what this is. So from the table in the textbook or another type of Laplace table, we know that we can just look up the inverse Laplace of this function right here. It's going to be a times kp, so it's the constant in the numerator, multiplied by 1 minus the exponent of negative t over tau p. Okay, and this is again in terms of deviation variable, and then if we wanted to know y of t would just be y naught plus, this value right here. Okay, so that's essentially what the transfer function is. And so now we know that we can have various processes where the input affects the output. So we can use the transfer functions to combine processes in a certain way. And so I'll show what that means right there. So if we know that we have an input which is a specified flow rate, and again we have a specified flow rate in a Laplace domain, this would be a variable. And so this variable, it's going to go through our actuator, and so our actuator will have a transfer function. We're going to call it GA of S. So this is the transfer function for the actuator, and this is going to affect the output. So the output of the actuator would be something like the flow, and so this can affect a process. So we'll have a transfer function for the process, and this will tell us how the input to the process, which is a flow rate, affects the control variable, and maybe this could be something like temperature. We also know that we can have various disturbances to a process, and various disturbances to a process will have their own transfer function. So this will be the transfer function of the disturbance. And so this could be something like this could be like a entering flow rate or something. So we'll just call this T naught. Okay, so T naughts, both of these are going to affect T. So the variable, maybe I should write it right here, it's going to be T. In the Laplace domain, this is going to be T naught in the Laplace domain, and then we might have a sensor, so the sensor can have a transfer function, and then coming out of here is going to be the sense temperature. All right, so we can look at this and we can see that all of these things, we can see that, by knowing these transfer functions, we can essentially determine how this parameter is affected by changing in F specified, or we can look at how T naught, changes in T naught affect this parameter as well. Okay, so we can define, or we can kind of group things together, and to do this I'm going to go ahead and say I'm going to call this term right here, let's see, I'll call this A in the Laplace domain, and I'll call this B in the Laplace domain, and these two kind of add together at this point to affect T. I'm just going to do this for simplicity. So essentially we know that T in the Laplace domain equals A plus B, all of these in the Laplace domain. We also know that this term G of S, or this term, what we care about really is this term coming out over here. So in general, this term T of S equals GS times what's entering TS, which we had defined from over here. Okay, we're going to eventually put all these things together, but I want to first start by looking at what is A. So A in the Laplace domain, right? So it's G, this transfer function equals output A over input T. Therefore, A equals the transfer function of the disturbance times the input of the disturbance, which is T naught. And then we also know that B equals, essentially it's going to be this input. So B equals the transfer function times F. F equals transfer function times F specified. So essentially I can say that B is going to be the transfer function of the actuator times the transfer function of the process times the input, which is F specified S. Okay, so essentially now this can be put in here, this can be put in here, and then we can write Ts, so the sense temperature, equals this transfer function G of S times T, right? So this right here is going to be AS plus BS times G, transfer function of the sensor. So again, I'll put A in there and I'll put B in there. So for the A term, I have this right here. So I would have GS. Okay, so we have the GS, which is out in front. I have to distribute that through, and then we have G of the disturbance times S times the input T naught S, plus also we have that sensor GS, and then times B, which is going to be GA, GP in the Laplace domain times F specified in the Laplace domain. Okay, so now what we can see here is that we have two specific types of inputs that there can be. We can have disturbance, or we can have with respect to the input to the process. So we can write two different transfer functions, right? So this transfer function right here, so this is going to be our disturbance, our overall effect of the disturbance. So this right here, I'll write G overall with respect to the disturbance S, right? Because this term right here equals the output, which is TS in the Laplace domain, over T naught S. Right, and so this right here, by combining these two transfer functions, the transfer function for the sensor and that for the disturbance, we can know how changes in this changes in T naught affect the sense temperature value. Right, and we would be treating that, and that would be considering that this term S specified stays constant. All right, and we also can say that this right here, G, this is going to be overall with respect to the set point, and so I can say G overall with respect to the set point in the Laplace domain equals the output, which is TS, over input, which is F specified S. All right, so here, these are two examples of writing overall transfer functions by combining individual transfer functions. So, and again, this tells us how the effect of the disturbance affects the sense temperature, and this would be assuming that this is constant. And then this transfer function talks about how changes in the input affect the sense temperature, assuming that this over here is constant. If they're both changing, we can combine them both together by using the additive transfer functions as shown there. There's a variety of ways that we can use that. We can talk about this with respect to PID control, and this will be something that we go to later. So transfer function for a controller is going to be the output. Output of the controller is going to be, the controller value over the input to the controller, which is the error in the process. And again, the error in the process is just going to be the difference between the set point and the sensed value. We'll come back to these things later. So if we have an error, the way an algorithm for a PID controller looks like is we have the proportional term, Kc. So this right here is just a constant, right? Or this could be, we could call this G, the transfer function with respect to the proportional term. And so these will eventually combine together in a certain way, and then we have a transfer function with respect to the integral term, so 1 over tau I s, and then we also have a transfer function with respect to the derivative term, which is shown here, tau ds. All of these things will add together and then the output from these is going to be the value coming out of the controller. And so this, you can think about this as something like, an air pressure or valve position or something like that. So we can combine these transfer functions all together. So we can just, if we look at to see, what is this term right here? So this is the output coming from this transfer function. So maybe I'll just define this to be A. This right here is going to be Kc times Es. Right, so that's going to combine together. We can maybe treat this term right here, we'll call this B, call this one C, or no, this one, we'll call it D, because we already use C over here. This is the control output. Okay, so this term B right here, essentially we have this term A going through this transfer function, so this is going to be Kc over tau I s times Es, and then we have this term D. It's going to be, so I should write Bs equals, so this term D equals, again it's going to be the same thing, Kc multiplied by, so it's going to be this term A multiplied by this transfer function Kds. And then so now for this term C of S, we multiply all of these things together, or we add all of these things together, and so we have the A, which is Kc times Es, plus Kc over tau I s Es, plus Kc tau d Es. Right, so now what we can do is we can factor out, so C of S equals, I'm going to factor out Kc and E, so Kc 1 plus 1 over tau I s plus tau ds, and I'm going to give us back this E at the end. All right, so the overall transfer function for the controller, for a PID controller, Gc of S, it's output over input, so it's going to be divide through by E. So if I take this and divide through by E, right, I'm going to be left with just this right here, Kc 1 plus 1 over tau I s plus tau ds. Right, this is the transfer function for a PID controller based on this logic flow diagram here, logic flow chart. Last thing we're going to come to later is when we start looking at, we'll look at closed loop feedback. So currently, up until now, through chapter 6, we're doing pretty much open loop processes where we change the actuator affects the process affects the sensor. For a closed loop feedback process, the system is going to look something like this, where we'll have a specified value of the output parameter, so y specified. Then we're going, so y specified will combine with so we'll subtract the sense value from the specified value, and this will give us our error. Okay, the error is going to is going to be the input for our controller. The output for the controller is going to be essentially the control setting. The control setting is going to go into the actuator. Okay, the actuator is going to provide the input to the process, US. So the process is going to have a transfer function, and then the output to the process is going to be YS. And so this is the variable that we care about. So this YS is going to be sensed. It's going to go to a sensor, and the sensor is going to give us the sensor variable in the Laplace domain. Okay, so we can also have things that affect the YS, or essentially that affect the process, and we can write this any number of ways. I can put an arrow here, or I can put an arrow here to maybe be a little bit consistent with what the textbook does. Is we can erase this. I'm going to erase this line right here. We can have this parameter coming from the process. So again, this is the output of the process. Well, no, I take that back. I don't like this form, so I'm going to do it the way that I wanted to do it initially. So this is YS that comes out here, so that's going to be the same value that comes out and the same value that goes down. We'll have a disturbance that can also affect the process, so there can be an input that goes through a disturbance transfer function that affects the process that gives us our YS value, and that's what's sensed from the process goes back. And so we can use the same logic, and I'm not going to go through this. You can look at this now if you want to. We'll come back and we'll derive this later. We can come up with a transfer function overall closed loop based on the disturbance that relates the output parameter YS over DS. Okay, and this would be like a regulatory control where, you know, we have a controller that's set up so that we can keep the process at a certain value. We can also do closed loop feedback based on set point changes, which is going to tell us YS over Y specified S. And this is like set point tracking or servo control, where, you know, we have changes in the set point affect the process, and the combination of the transfer functions. So again, we'll have to, you know, combine these transfer functions in a way to come up with an overall transfer function for this process that'll tell us how the output is affected by here. You know, same as the disturbance, we can kind of go through the disturbance to determine how the disturbance affects this. But you can also see that this term right here, it's affected by both the disturbance and it's affected by the controller. So we have to be a little bit careful in how we define it. Just wanted to introduce that here, and if you want, you can, you know, think about how to derive those for each of those processes. And this is going to be very general. So, you know, we know that this transfer function for the actuator can be different. The sensor can have various transfer functions, and then this is something that we derive based on our process models. Typically for the controller, we're going to use PID control. It could be P only, PI, or PID, but these are things that we're going to revisit a little bit later. All right, let's spend a minute maybe reviewing stability of a transfer function. So again, we know the transfer function, it's the output over the input. When we talk about stability, we can talk about representing this in terms of the numerator and the denominator, and the behavior of the denominator is what determines the stability or the dynamics. Okay, so we'll first just start with an easy case. So we have a first order transfer function. So if the transfer function is a first order process, it's Kp over tau ps plus 1. Okay, so some of the things we're going to assume right here is that tau p is always greater than 1, or greater than or equal to 0. So tau p has to be a positive number. You can't have a negative time constant because things don't go reverse in time. Kp can be plus or minus. So if Kp is positive, that just means a positive change in an input leads to a positive change in the process. If Kp were negative, a positive change in the input would lead to a negative change in the output. And you can think about the difference between the two, whether or not you're using maybe steam or cooling water to affect the heating or cooling of a process. But again, this term is always positive. Therefore, if we have a first order transfer function, this term right here is always going to look something like this form, right? So ignoring what this is always going to look like this type of form. So this is going to give us essentially a KP. We'll call this KP. Let's just do a little bit of math. So I'm going to divide everything through by tau p just to make it look like the table. So this is going to be s plus 1 over tau p. Now this is not standard form, but if we use this to look, if we do the Laplace table, something that looks like this, we take the inverse Laplace of this function, right? The inverse Laplace of this is going to be kp over tau p times the exponent of, again, negative t over tau p, right? And so therefore, a first order, if we have a process that's an ideal first order transfer function, this is always stable, and the dynamics is such that it'll always have exponential decay to the new set point. So that's the performance generally of a first order transfer function. Last time we looked at second order transfer functions, third order transfer functions, and for the sake of this class we won't go much above that. If you have a third or fourth order or point order transfer function, you can use the Routh-Array criteria to determine the stability. Let's now look at the case where we have a general transfer function, and we said last time, again, we used something that was sort of generic. So if we have a third order transfer function, we know that we can always factor out a real root. So it would look like this, s plus a, and then s squared plus b s plus c. So if this is the general form of the transfer function, right, we know that we can do things like partial fraction expansion, or we can kind of separate out these terms to give us something like c1 in the Laplace domain over s plus a plus c2 over s squared plus bs plus c. And if it doesn't look exactly like this, you can always factor out constants, put them out in the front, and they're just going to affect these terms up here in the numerator. So again, looking at this term right here, as long as this is s plus a, right, or we can call this a negative root. So s plus a in the denominator would have a negative pole, so that would mean that a value of s equals negative a makes this term go to infinity, right? As long as this term is positive, this is the inverse Laplace is going to be exponential decay, negative at. All right, and we showed that last time. And again, we also showed that as long as these terms right here are both positive, right, this is going to lead to stable behavior. And then again, we looked at, we can compare the relative values. So again, we can determine the roots of this quadratic, and if this quadratic has imaginary roots, there's going to be oscillations. So I guess I should say, so first, if both of these are positive, it's going to be stable. If any one of these terms is negative, it'll be unstable. Right? Then when we factor this out, so if there's imaginary roots, that means the process is going to have oscillations. Okay, but then both of these have to be positive still. The real root has to be positive for it to be stable, and it will be if these are both positive. There's no negative values there. So that was just sort of a quick overview. Again, if we can again look at something. If this is ns, and if it's written in terms of a3 s cubed plus a2 s squared plus a1 s plus a0, our options here is we can plot this function, and we can determine what is the real root, and we can factor it out to get here, or we can use the Routh-Array criteria, and we discussed the definition of that before. Just quick overview of stability. So now I want to go through and actually do an example of deriving a transfer function for a process. Let's consider a composition mixer. We'll look at this process. So we have two streams that are going into a well-mixed system. I'm going to put the valve on stream 1. So maybe this is our input, is the flow. And so in stream 1 we have F1 and C1. And then we have another stream that has a different flow, F2, and different composition, C2. Now coming out, we have of total flow rate and a total composition F and C. And so we're going to make some assumptions here. And so one assumption is going to be constant volume, right? If I ask you how we make this constant volume assumption, or how we achieve this, you could consider the fact that we would have essentially level control, and we could put a valve on the outlet and detect the level, and any changes of level we can open or close this valve coming out. So we can achieve constant volume for this process. We'll maybe also assume constant density and some other things, and we'll introduce those coming up. So for again, we can write the transfer functions for the process, or for the actuator. We might have a sensor, composition sensor on the outlet. We could do the transfer function for that. It would probably be like a dead time type model, and we can derive the, so this would composition model. We have first order actuator. We know those transfer functions. We need to come up with a transfer function that relates changes in composition with changes in F1. So for this overall process, we can change F1 and we can get composition. So our overall process transfer function is going to be composition coming out over F1 entering. Okay, we also know that F equals F1 plus F2, okay, because of our constant volume assumption. So we're going to go ahead and derive the balance for this process first. So we know that we're going to have so that we have to do a mole balance. So I have the derivative in the number of moles dt equals, so I'm going to use volume. I'm going to say the F's are in terms of volumetric flow rate. So that's another assumption, or that's another designation or use. We can, if we have it in terms of mass, we can convert it to volume just using the density. So the flow, so the entering number of moles is going to be F1 times C1 plus F2 times C2 minus the moles coming out is going to be F times C, but we also know that F times C is going to be F1 times C minus F2 times C. That gives us the composition coming out. So one of the things that we can note is that, okay, so F2 and C2, these terms right here are just treated as constants. C1 is being treated as a constant. So we have this taken care of, but notice right here we have two functions multiplied by each other. So this is a nonlinear term, and so for this nonlinear term we have to go ahead and linearize it. Okay, so the first thing we have to do is, in order to come up with a transfer function, we have to linearize nonlinear terms. So we're going to approximate F1 times C is going to be equal to, so it's going to be the value at the initial condition. So this is going to be this is going to be F1 naught times C naught. So remember, C naught is the composition inside the tank at steady state before a change is made to the input. Plus, so we're going to have the linear term in terms of concentration. So this is going to be C minus C naught times the derivative of the function F1C with respect to C, evaluated at the initial condition F10 is C0. Plus, we're going to have the linear term with respect to the flow, which is going to be F1 minus F10, multiplied by the derivative of the function F1C with respect to the flow F1, evaluated at F10 C0. Okay, and now this is going to essentially give us F10 C0, so the initial combination of the two, plus this next term is going to be take the derivative with respect to concentration. We get F1 evaluated at F10. So here we have F10 C minus C0 plus over here we're going to have again C0, which is the derivative evaluated at the initial condition, times F1 minus F10. And then again we can further simplify this combining these things together. Okay, this is going to be F10C0 plus F10C minus F10C0 plus F1C0 minus F10C0. So F10C0, these terms are going to cancel off, and this will kind of give us negative F10C0 plus F10C plus, and I'm going to write this one as C0F1 because, again, this is our function, this is a constant, function, constant, so this is all linear with respect to the parameters. All right, so going forward a little bit, we're going to put these, okay, we also know up here that n equals, or n over v equals c, so n equals cv, so this term right here is going to be v times dc dt. So now we'll have v times dc dt equals, plug that, so we're going to have to plug that approximation in above, and so we'll have F1C, we have F1C1 plus F2C2 Okay, so now I'm going to combine these together, and we'll have V times dc dt equals, this is going to equal, let's see, F2C2, so this was a constant from my equation, plus F10C0, this was a constant from the approximation, plus C1 minus C0 times F1 plus F2 plus F10, actually this should be minus F2 plus F10 times C. Now you can kind of go ahead and check in, but I just kind of rearranged it so that I had a all my constants were up in front, and then I had my constants in front of my input function, and then my constants in front of my output. Okay, so now from here to derive our transfer function, what we can do is we can put things in terms of deviation variable. Okay, so in other words, we'll say that C hat equals C minus C bar, which is the initial steady state condition, or this, we call this to be C0. And then we can also say F1 hat equals F1 minus F10. Okay, put these in terms of deviation variables and then plug them up into this equation. The next thing we can do is we can apply the steady state condition. So what by that I mean is we solve this, we write this equation at steady state, which starts off like dc0 dt. And again, at steady state, the rate of change is 0 equals, and then we just essentially write this whole thing in steady state condition, and you'll see that we'll have to, we'll write the constant, and this is still valid, and at steady state condition, our variables, at steady state conditions, we have stuff, and then we just have to write that our variables would be F10, and whatever this variable would be C0. I'm not going through this in entire detail because this is a homework problem for this class. So we apply the steady state, we subtract the steady state, and then the next thing we do is then again we take the Laplace, and then once we take the Laplace we just do a little bit of work and we get our transfer function for this process, which is the output, which is C of S over F1S. Okay, so that's how we get the transfer function for the process model that we derived for this process. There's actually an easier way to do it. We can also take the transfer function using equation 5.7.3 from the textbook, and if this is something that you're not familiar with, maybe you can make a note of it somewhere, This will simplify deriving the transfer functions or solving for the transfer functions for any process, including nonlinear processes. So in the case, this equation tells us that the transfer function, which is ys over u of s, in general equals the partial of the function with respect to the output and the input, the partial derivative with respect to the input evaluated at the steady state or initial conditions over s minus the partial of the function with respect to the output evaluated at the initial conditions. And the important thing is that our function f of yu has to be written in terms of dy dt equals. So if we have any constants here, we have to move them around and do that. So going back and now looking at what our function is. So again, I'm going to just start from here, from this term. And so this would give us the equation. So this n is equal to cv. So we have, again, v times dc dt equals f1 c1 plus f2 c2 minus f1 c minus f2 c. So again, we need to go through and divide. So let's first over here, we're going to identify this f1 is a variable, f2 and c2, these are just constants, variable, f2 is a constant, c is a variable. So I'm going to go through and divide by v. So divide by v, I'm going to call this 1 over v, and over here divide by v. So now I have to take the first partial, so this first partial, and I'm going to just give myself an arrow. So the partial derivative of this function with respect to f1, which is the input, so the partial of this function over here is going to be, partial of this term is going to be c1 over v. Partial of this term with respect to the input, so this is just a constant with respect to the input, is 0. Partial of this with respect to the input is going to be minus c over v evaluated at the initial condition, which we had called c naught. And then the partial of this term with respect to the input is also 0, so this is going to be let's see, c1 minus c0 over v as our top term up here. Okay, so now we can do the same thing for this one. Take the derivative with respect to the output. So the first term, it's a constant with respect to the output, so that's 0. This is also a constant. The next term is going to be minus f1 over v evaluated at f1 0. Derivative of this with respect to the output. And then this last term, derivative with respect to the output, minus f2 over v. And so again, this is going to be minus, in the parentheses, f10 plus f2 all over v. So now when I go ahead and get the transfer function for this process, it's going to be essentially c1 minus c0 over v all over s minus. Since this is minus, this is going to become a plus, f10 plus f2 all over v. Okay, so this gives us the and then again we can simplify this a little bit, but this shows how we can apply this equation and make deriving the transfer function pretty straightforward for this process. So that's all I wanted to do for today. Stop there, and we'll talk to you next time.